All right, welcome guys. Today we're going to be talking about exponents and logarithms. We will start first by talking a little bit more about exponential functions, and then we'll look at some logs. We'll talk about the laws of logarithms as well. Moving on from that, we would then look at solving equations using logs. And then we'll also end up with some exam style questions to help make the process a little bit easier, especially when you're on the test. All right, so let's first start off here by talking a little bit more about exponential functions. All right, so we have exponential functions. Okay, what are exponential functions? Well, there's a broad definition for exponents here, and you guys already know what exponential functions are. They occur around us naturally. For example, let's say when a cell multiplies or when a cell doubles. Same thing with radioactive decay, right? Those are all exponential. They are involved in exponential functions, right? So in its definition here, at its very core, what we usually end up with is some sort of base here with some value raised to the top that we call the exponent, right? That's the broad definition of it. We do have a general form, though, of an exponential function, and that is that if we call y as equal to a to the power of x, well, in this case here, a has to be greater than 0, right? The base here has to be greater than 0. And generally, too, a cannot equal 1. Usually, if you have an exponent here of 1, well, that wouldn't really make sense because if you take 1 and you raise it to the power of 3, you still get 1 times 1 times 1, which is 1. If you did 1 to the power of 4, you still get 1 times 1 times 1 times 1, which is also 1, right? So in this case here, there's no use in having a base here that is equal to 1. Quantities that increases exponentially or decreases exponentially are going to do so very rapidly, right, as we're constantly doubling it. So at this very core here, one of the things to make sure we're understanding when it comes to exponents, before we even get to our exponential rules, is to understand a little bit more about exponential increase and exponential decrease, or exponential growth and decay. If it is a growth here, it's going to be represented in this form, whereas decay here is going to look more like this one, right? The values are going to get smaller and smaller as we go down. Let's now look at our exponential rules. Our exponential rules are perhaps the most important part of this entire lesson. This is what's going to allow us to solve out and derive some of the logarithmic rules that come along with solving some of these questions. And so it really pays to make sure that we understand the exponential rules all the way through. I always like to start off here by talking in terms of just the basic. Let's say, for example, if I have 2 to the power of 3 and I multiply by 2 to the power of 4, what would that give us? Any high school student here looking at this, you guys can probably tell me right away this is just going to be 2 to the power of 7. But how did you know that it was 2 to the power of 7, right? This is just going to be 2 times 2 times 2. This 2 to the power of 4 is going to be 2 4 times, 3, 4. So this first part here, there's that. And the second part here is that. Now I go ahead and multiply all of them together. This is just going to be 2. And how many times am I multiplying it? I'm doing it 1, 2, 3, 4, 5, 6, 7 times. Right? And so to make life a little bit easier here, I'm going to put the rules up on the top right here to make sure we can always come back to it if we need it. So in this case, all we solved here and described was that if we have a value a and we raise it to the power of x, and we have another value a, base a, and raise it to the power of y, if we're multiplying and the bases are the same, the bases have to be the same, we can go ahead and add the exponents. Okay. All right, let's go ahead and look at the second rule here. Well, if I have, let's say, 2 to the power of 5, and I'm dividing it by 2 to the power of 2, what would that look like? Well, that's just going to be, the numerator here is just going to be 2 5 times, so 1, 2, 3, 4, 5. The denominator is going to be 2 times. Now, here's another important rule to also think about. You can only cross things out in the numerator and the denominator if you are dealing with multiplication. This does not work if you're dealing with addition or subtraction. I have seen way too many mistakes from students on that. Make sure if you're crossing things out that you're dealing with multiplication. There's a 2 in the numerator here. There's a 2 in the denominator here. I can cross it out. There's another 2 in the numerator, another 2 in the denominator, so I can cross it out. So what am I left with? I am left with 3 2's in the numerator, right? So in this case here, that's going to end up being 2 to the power of 3. So what do we end up with here? This says here if we have a raised to the power of x, and I divide it by a to the power of y, I'm going to get a x minus y. Right? Now this rule has some implications. So what happens here if I have 2 to the power of 2 divided by 2 to the power of 5 this time? It's still going to work out the same way, right? We are still going to have 2 2's on top. We're going to have 5 2's at the bottom. 3, 4, 5. And now we do the same thing again, right? Cross out your numbers on top, cross out the numbers at the bottom. Remember, this only works because we are dealing with multiplication. And so I end up with 1 in the numerator, right? And 2 to the power of 3 in the denominator. Well, we said here that when we are dividing, we subtract. And so in this case, this therefore has to be the same as 2 to the power of 2 minus 5, which ends up being 2 to the negative 3. And so what we've proven here is that if I have a base raised to a negative exponent, that just means 1 over that base to that particular exponent. I like to think of it like this. If you see a negative and it's in the numerator, put it in the denominator. If it's in the denominator, put it back into the numerator. So now we've talked about, some days we like to call that the product rule. The first one, the product one, the second one, the quotient rule. And so there's the third one as well. Right? The next one here, for the sake of time here, if you have any base raised to the power of 0, that's going to end up equaling 1. Another part here to make sure you guys have down is if we have the square root, right? The square root can be converted into an exponent by remembering that this square, just like what the name represents here, is actually supposed to be a 2 in front of it. We just leave it because of just basic convention. We all know if we say a square root, there's going to be a 2. It's to the power of, it's going to be a 2 in front of that. It's a, we know that that's just going to be to the second root, right? So in this case here, this is going to be x to the power of 1 over 2. Okay, let's try out another one here to make sure you guys have got it down. What if it was the cube root of x to the power of 5? That's going to be x 5 over 3. This is a very important rule to make sure you understand, right? Now that we've talked about the basic rules here, we are now ready to dive into some more of our logarithms. All right, so let's talk about logarithms by first proving why we need logarithms in the first place. For example, if I have, let's say, p to the power of 3, and I say that that's equal to 343, what's p going to be equal to? Well, this one's very straightforward to solve, and I'm sure most of you guys can solve it out. That's just going to end up being, we're going to take, because it's p to the third here, we're going to take the cube root of both sides, okay, cube root of both sides, and then the cube root, you can use your calculator here, the cube root of 343 is going to end up being equal to 7, right? That's a very straightforward one. Most of you guys could have probably gotten that just fine. Now, consider this one. What if I had 3 to the power of q, and I said that was equal to 343? Okay, so now we have a base of q, of 3, with an exponent of q, and we're trying to find out what number that had to have been for us to get that 343. So to do this here, we need to find the power of 3 that gives 343. One way to kind of do this is just through trial and error, right? Obviously, by using trial and error, this thing is going to take forever to solve out. because you're going to have to test it out to see if it works. Try out a different number, try 6, try 7. It's going to take forever. To avoid using the trial and improvement, the trial and error method here, we need to define the power y, to which gives a base a. All right, so here's where the log part comes in. So now let's take this into consideration. I'm going to call this y is equal to log base a of x. The way we say this is y is equal to the logarithm to the base a of x. So now let's see how the two expressions here, the logs and the exponents, can be bridged together to help us solve the question on the right. So watch this, guys. Y, I'm going to use different colors here so you guys can see it. Y is equal to the log base a of x. If I was to convert it over to our exponential form, here's what that looks like. This is now going to be a of y is equal to x. Take some time now to make note of where the values are placed when we're moving from the logarithmic scale over to our exponential scale. To make your life a little bit easier, start off with the base. That little number becomes the big number. That's one way to just make your life a little bit easier. The next part here is to recognize that the number next to the a is going to now be on the other side. And then the y here is going to be the exponent. Okay? So to simplify this down here, the way we call this is going to be y is equal to the log base a of x. And therefore, that's going to be the same thing as taking a, right? The little number becomes the little letter becomes a big letter now. A to the y is equal to x. For example here, if I have 2 to the power of 5, which we know that to be 32, I can switch it back to the log form here by calling it log of 2 to the 32 is equal to 5. Okay? In fact, these two things are inverse. When we look at them and compare them together, they're going to be inverses of each other. So it's important to think about it. So that gives us another implication here. Y is equal to, if y is equal to the log base a of x, and we now know that we can interchange them as a to the y is equal to x. Well, if I have the a and I raise that to the log of a of x, that's going to undo the log. So see what's going on here. I have the exponent, and I'm now taking the exponent of a log. I'm going to undo that, and I'm just returning with that value there. Same thing on the other side. If I have the log a, and I take that as an exponent here, I'm going to be returned with just y. So for example here, if I have 7 log base 7 of 2, because I'm taking, this is an exponential function, and I'm doing that in conjunction with my log function here, that's going to be returned as 2. All right? And likewise here, if I have log base 3 of 3 to the power of 6, that's going to undo each other, and then end up with just 6. All right? So in the first example here, we're just raising 7 to the power. That 7 must be raised to give us 2. And therefore, that must end up being 2 for it. All right. Let's now start off by talking a little bit more about the laws of log. All right, so we're going to talk about our logarithmic rules here. Okay, our first implication here that we have to understand before we move on is the fact that anything a raised to the power of 1 here is just going to be a. Anything raised to the power of 1 is just going to be that thing by itself, right? And so therefore here, in logarithmic form, log base a of a is going to be the same thing as just 1. Right? That's important. So I'm going to put that over to the top right here. Log base a of a is going to end up equaling 1. Likewise here, from our exponential rules, we know that anything raised to the power of 0 is also going to end up being equal to 1. Okay? So in this case here, log base a of 1 is going to end up being equal to 0. Right? So that's 1, there's 2. Log base a of 1 is going to end up being equal to 0. If we can remember these two rules here, then it's going to be a little bit easier, especially when we start talking about the multiplication law. So let's take a look at that. Multiplication law. The multiplication law here states that if we let m equal the log base a of x, and we let n equal the log base a of y, we know to convert this first one here into our exponential function, that's going to be the same thing as x equaling a to the power of m. Right? And y is going to be equal to a to the power of n. If I go ahead and multiply these two together, that's going to end up being xy is going to be equal to a to the m times it by a to the n. We've already mentioned here that if we are multiplying exponents, we can add. So that's going to be the same thing as a to the m plus n. So in this case here, m plus n is the same thing as the log base a of xy. But we also know that m is equal to the log base a of x, and that n is equal to the log base a of y. And so in this case here, we end up with log base a of x plus it by log base a of y is going to be equal to the log base a of xy. Right? So that takes care of our third rule here, which just says here that if we have the log base a of xy, that's going to be the same as the log base a of x plus it by the log base a of y. Right? Once again, tying into the fact that these two share a very intimate relationship with each other. They're inverses of each other. Let's go ahead and talk a little bit more about the division rule here. Let me use a different color here so we can distinguish the two of them. The division law. Division law. Okay, let's take a look and see what that one's saying here. If once again we let m be equal to the log base a of x, and we let n equal the log base a of y, then we know that x is equal to a to the m, and that y is equal to a to the n. Well, we also know that x over y is going to be equal to a to the power of m divided by a to the power of n. What happens when we are dividing exponents? We subtract. Right? That's going to be the same thing as a m minus n. And so now, do the inverse, just like what we talked about here, and we end up with m minus n is equal to the log base a of x over y. Once again, we already know that m is equal to log base a, so therefore we're going to have the log base a of x minus it by the log base a of y is equal to the log base a of xy. Right? So that's going to be the fourth rule right here. These rules are paramount. You got to know these. Okay? Log base a of x minus it by log base a of y. All right, so I went ahead and posted the the rules again on the right-hand side, and we're going to continue building on to that. So far we've talked about the multiplication rule, we've talked about the division rule, and now we're also going to talk about the power rule. So let's take a look at it here. Power rule. All right, the power rule states here, once again, if we let m equal to the log base a of x, we know that x is going to be equal to a to the m. If we have x to the power of n, then therefore that means that I will have a to the power of m raised to the power of n. Using the power law for indices here, we can see that x to the power of n is going to be the same thing as a to the power of m times it by n. We went over this rule at the beginning. Writing this in log form, we get m n is equal to the log base a of x to the power of n. But we also know, right, that m is equal to the log base a of x. And so in this case, n log base a of x is equal to the log base a of x to the power of n. So what we've proven here for the fifth rule here is the fact that if we have a log base a, let's try it out that way, log base a to the x to the power of n, that's going to be the same thing as moving that n over to the front, n log base a of x. Now that we've discussed all of the rules here that you need to understand, let's see how we can apply these laws to help us combine several logs together. So here's the question. Express this as a single log. Okay? Let's see what we're working with here. So in this case, we're given the answers, and we're just going to have to try to convert it back into one single log. And we can do that. Let's take a look and see what we have. For this one, which rule are we going to use to solve this one out here? Well, that rule here is going to be rule number 5 that we looked at. This is going to be the same thing as the log base a of 3 to the power of 2, right? Just like what that one says. Okay. So that takes care of that one. Now let's go ahead and try the next one. The next one here is going to be log base a of 2. There's really not much that we can do with that one, right? So in this case, that becomes a log base a of 2. But what about the next one? That's going to be minus 2 log a of 6. That's going to be minus log base a of 6 raised to the power of 2. Let's go ahead and simplify this down. This can be simplified down to the log base a of 3 times 3, which is going to end up giving us 9, plus it by the log base a of 2, minus it by the log base a of 36. Using rule number 3 and number 4, using our multiplication rule and our division rule, let's start with the multiplication rule here for these two. That's going to be the same thing as the log base a of 9 times 2, right, because we're multiplying here. And they're all being divided by 36 because we have a subtraction there, right? Simplifying that down here, that's going to be equal to the log base a of 18 over 36, which is going to be the log base a of 1/2. All right, let's take a look at this next question here. We're going to try to see if we can expand this particular equation. So we have the log base 10 of a to the power of 2, b to the power of 1/2 divided by c to the 4th. All right, let's see what we got here. We first know we have division, and so in this case here, we're going to subtract those two from each other. So that's going to be the log base 10 of a to the power of 2, b to the power of 1/2, minus it by the log base 10 of c to the 4th. The next part here, we can see that these two right here, are being multiplied together. And so in this case, we can add them. Log base 10 of a to the power of 2 plus it by the log base 10 of b to the power of 1/2 minus it by the log base 10 of c to the 4th. We can still keep going using rule number 5. This is going to end up being 2 log base 10 of a plus it by 1/2 log base 10 of b minus it by 4 log base 10 of c. Logarithmics, logs with a base of 10 are usually written as just log. So if the log has a base of 10 here, we just call that the common log, and most of the time here it's just going to be written as just log, right? Or some days in unconventional places you might see LG here, right? That's just going to be the log. So therefore we can rewrite this whole entire expression here as 2 log A plus 1/2 log B minus 4 log C. So while there's nothing stopping us from, let's say, having a log with any positive number, there are usually only 2 commonly used ones. And that's going to be the log with a base of 10, which we've talked about, right? We just call that the common log. And we can also have the log with a base of e. And some of you guys might be able to remember what e stands for, right? Remember that e is going to be an irrational number here, right? And its value is going to be 2.718. And also, too, thinking about e, remember that if we have y equal e to the x, and we also have y as being equal to the ln of x. And this is something that we'll go into more details as we go. But remember here that the log base 10 can be found on your calculator. When you click that log key on your calculator, that's going to be to the base of 10. The one with the base of e is sometimes called the natural log, and that's the convention here. So instead of writing the log base e of any particular number here, we just end up calling the ln of x. Right? So we just call the natural log, and it has many, many applications in math and science. So I already just mentioned here that the log button on your calculator is going to be to the base of 10. Now, what if you were to find, let's say, the log base 5 of 8? Now, you can't readily do this in your calculator because if you click that one, that's going to be a base of 10. However, we can change the base of the logarithmic as follows. So if we have x equal the log base 5 of 8 here, we know that's going to be 5 to the x, and that's equal to 8. So taking the log base 10 up on both sides here, we end up with the log base 10, 5 to the x here, as equal to the log base 10 to the 8th. We already know these rules. That's going to be x log base 5, and that's going to be equal to the log base 8. And so therefore, x is equal to log base 8 over the log base 5. Wow. Here's what we just proved. So we just said here that if you have the log base 5 of 8, you can use the log base 10, but this would just end up being the log base 8 divided by the log base of 5. All right. So in this case, you can still change the base if you need to. Remember the rules though, right? We just went from, and I'm going to write it out again here so you guys can see it a little bit better. The log base 5 of 8 is going to be the same thing as the log base 10 of 8 divided by the log base 10, once again, of 5. Make note of where the numbers went, right? The smaller one here is in the denominator. This bigger one here is in the numerator, and now they have a common base in between the two of them. And if you were to do this on your calculator, log base 8 divided by log base 5, you're going to end up with, about, if you round to the third sig fig here, that's going to be 1.29. All right. Now, what if we did the exact same question, but now instead of using the log base 10, we're going to end up using the log base e instead. So in this case, this becomes the log base 5 of 8. And we know that to be the ln of 8 over the ln of 5, right? This is going to be the natural log. It's still going to end up giving you 1.29 here. In general, to find the log base a of b, if we let x equal the log base a of b, we can rewrite it out. See if you can solve it out. Take a pause here and see if you can solve it out. A to the x is equal to b. Taking the log to the base c for both sides, we get the log base c of a to the x equals the log base c of b. This is from the previous slides here. We know that to be this, and we know that to be this as well. And so therefore, x is equal to the log base c of b over the log base c of a. Once again, make note of where the numbers are going, right? Make note of the fact that the log base a of b ends up being the log base c of b over the log base c of a. As always, guys, as you're watching these videos too, feel free to comment down below here. Let me know if there's things that you like, things that you'd like me to do more of. It just helps me make better videos. All right, so now that we have mastered the rules here, we can now use our laws of logs to help us solve some of these questions down. Okay, so to solve this equation, we have log base 5 of x plus by 2 is equal to the log base 5 of 10. To solve this equation here, we have to write the constant value 2 in logarithmic form. So we know that 2 is going to be equal to 2 log base 5 of 5. Why is that? Because we know log base 5 of 5 is just going to end up equaling 1, so we didn't really change anything, right? Log base 5 of 5 is going to end up being 1. So in this case, we didn't really change anything. So now we have the log base 5 of 5 to the power of 2. And so that's the same thing as the log base 5 of 25. Now the equation can be rewritten as the log base 5 of x plus by the log base 5 of 25, and that's equal to the log base 5 of 10. Okay. We can now combine these two together. This gives us the log base 5 of 25x, and that's equal to the log base 5 of 10. Okay. This is now going, they both have logs on both sides here. So in this case here, this is the same thing as 25x is equal to 10. And then x just gives us 0.4. Review this again, take a pause it and rewind if you need to, but really, really make sure that you understand this question all the way through. Let's try our hands on solving equations in the form of a to the x is equal to b. So find x to 3 significant figures if b 2 to the x is equal to 30. Well, we can start by just taking the log on both sides. So in this case, this becomes a log 5, to the power of 2x here is equal to the log of 30. Move that 2 to the front, that 2x to the front, 2x log base 5 is equal to the log of 30. We have 2x here is equal to the log of 30 divided by the log of 5. And then we now know that x is going to be equal to the log base 30 of 2 log base 5. Remember, we're dividing by 2, so that's going to be end up being in the it's going to be in the denominator. Avoid using calculators when you're working with logs until the very last stage, okay? Because since the numbers that you're working with are not going to be exact, this will help you avoid errors due to rounding. Okay? This equation that we just worked on here can also be solved with a base of e. right? So check to see if you get the same solution and comment in the chat box at the bottom there. Let me know how it goes. Let's take a look at another problem here, which is a bit on the advanced side, but it's still the same idea. Find x to 3 sig figs if 3x plus 1 is equal to 7x plus 2. As always, start off by taking the log on both sides. Log 3x plus 1 is equal to log 7x plus 2. Move that 3x plus 1 to the front. 3x plus 1. Log 4, I'm sorry, not base 4. And that's going to be equal to x plus 2. Log 7. We know that we are multiplying here. And so in this case here, we can go ahead and expand it a little bit more. And this is going to end up giving us 3x log of 4 plus log base 4. Right? Remember, guys, it's just going to be your distributive properties. Right? And that's going to be equal to x log 7 plus log 2, I'm sorry. There should be a 2 in front there. 2 log 7. From here, we're going to group like terms. So we have 3x log 4 minus it by x log 7. And I'm going to set that equal to the other side here, which is just going to end up being 2 log 7 plus a minus log of 4. Factor out your x, 3 log of 4 minus it by log of 7, and that equals 2 log of 7 minus it by log of 4. Divide out your 3 log of 4 minus it by the log of 7, and we end up with x is being equal to 2 log base 7 minus log 4 here, divided by 3 log base 4 minus it by the log of 7. All right, let's try this next question out here. Solve 3 to the power of 2x minus it by 5, 3x plus 4 equals 0 to 3 significant figures. Okay. Well, let's first start off by letting y equal 3x. Right. So if y is equal to 3x, then we can rewrite this equation, this top equation here, as y squared, right, minus it by 5y plus it by 4. That's equal to 0. You have your factors. What are your two factors here? Two numbers that add up to give you -5 but multiply to give you 4. Put the answer in the comment section here if you know it. That's going to end up being y minus 1, y minus 4. Right? So our solutions here are y is equal to 1 and y is equal to 4. Remember here that the solution and the factors are going to have the same magnitude but different signs. Okay? So in this case here, this becomes 3 to the x is equal to 1, or 3 to the x, if we factor it back in, is equal to 4. Okay? So if 3 to the x is equal to 1, therefore we know anything raised to the power of 0 is going to end up being 1, so x has to be 0. So now solving for 3 to the x is equal to 4, we can now plug it back into the log form here and simplify it down, right? X log base 3 is equal to log base 4. X is going to be equal to the log base 4 divided by the log base of 3. We just finished talking about some exam style questions And lastly, I wanted to leave you guys with applications of this, right? So common logs are very useful, as we saw here, in representing really big numbers or really tiny numbers. In chemistry and biological sciences here, most of the time we're dealing with pretty low concentrations of either hydroxide ions here or hydrogen ions, right? So in this case here, the P, think of that as being the negative common log activity, right? So in this case, this P here represents the negative log. Log base 10, obviously, it's a common log, right? So in this case here, what we end up finding is that the pH is going to be equal to the negative log of the concentration of our H plus ions. What I mean by that is, in solution, if you have, let's say, an acidic compound, it's going to split up, it's going to dissociate, what we like to call dissociate completely into its individual parts here. You will have your H pluses in solution. And what we're doing here is testing the concentration of the amount of hydrogen ions that we have in there, right? So in this case here, the pH is going to be represented by the negative log of the concentration of our H plus ion. So therefore, looking at the relationship here, notice that it's a negative log. And so as a result, as the hydrogen ion concentration increases, we expect the pH to decrease, right? And this is also why it's really important, because we're dealing with bases of 10. This is precisely what makes our acids so dangerous. Same with the bases as well. Because we're dealing with things on the logarithmic scale, for example, if we're moving from, let's say, a pH of 4, or a pH of 7, I'm sorry, which is neutral, to a pH of 4, if I was to ask you this question, how much stronger is that? Right? How much stronger are we moving from 7 to 4? Yeah, most people might just say, well, it's just 3, right? So in this case, we're going from 7, we're going down to 4. So that's 3. But it's actually, hold on tight, guys, it's going to be 1,000 times stronger, right? Why is that? Because we mentioned here that this is the log base of 10. And so in this case, that decrease there, the pH of 4 implies that the concentration of the protons here would be 10, right? Let me write it down here so you guys can see it. If we have the pH as equal to 4, that's going to be the negative log of the concentration of H plus ions is going to be equal to 4, right? That's the same thing as saying that's 10 to the negative 4 is equal to the concentration of H plus ions. Remember the common log, so I'm not going to put the 10 there, but you guys already know that represents a 10. Whereas if I was to do the pH of 7, that's going to be the negative log of the concentration of H plus ions as being equal to 7. So once again, that's going to be 10, base 10, to the negative 7 is going to be equal to the concentration of our H plus ions. Right? And so in this case here, this is going to be a factor of 1,000.